Good afternoon, and welcome to the Center for Environmental Policy in the School of Public Affairs webinars on mitigation, a sectoral approach, which we are co-sponsoring with Energy Innovation. We are very pleased today to have with us Jeffrey Rissman, who is the Director of Energy Innovation's industry area and the originator of the Energy Policy Simulator. He has a background in environmental science as well as in city planning, so he's very well equipped to lead us on a discussion of the industrial sector, which may be the worst in terms of emissions generation. And just, I guess, a final introductory statement is I just learned that that Jeffrey Rissman is the author of the book Zero Carbon Industry, which will be coming out probably at the end of this year with the Columbia University Press. So indeed, we're very happy to have you, and thanks for joining us.
Thank you so much, Todd. I'm really happy to be here and excited to share some knowledge about decarbonizing industry. I'll go ahead and share my screen. I get host disabled participant screen sharing when I click the share screen button. All right, let me know, can you see the slides come up?
Yes.
All right, so as Todd mentioned, I lead the industry program at Energy Innovation, which is a nonpartisan think tank, a policy research firm that researches technologies and policies that can help decarbonize all sectors of the economy. And today we'll be talking about industry. So this is the book Todd mentioned, Zero Carbon Industry, and my materials for today's presentation are actually drawn from this book. It covers the entire roadmap of how to understand the global industrial sector, its energy use, its emissions, the technologies, and the policies that will bring emissions down to zero. This is the high-level table of contents, which I'm showing you because it's also effectively an overview of the major steps and things to do and understand in order to decarbonize industry. I won't read it all off to you, and in today's presentation, I can't, of course, cover an entire thick book's worth of material. We're going to focus on certain parts that are important and good for an overview. We're going to cover some of the overview materials from the first chapter. We're going to do a deeper dive into direct electrification of industrial processes, which is very important and sometimes overlooked, particularly with a push to use hydrogen now in the US and in Europe. We'll do a high-level look at some of the policies. So without further ado, let's jump into the overview. Here's a glance at global greenhouse gas emissions by sector. Here we're allocating the emissions from purchased electricity and heat to the sectors that used that electricity and heat, overwhelmingly electricity in the US. And you can see that after reallocating the electricity to the purchasers, industry is about a third of global greenhouse gas emissions, which is well more than any other sector. And if you look at where industrial emissions are coming from, about 45% of the globe's industrial emissions come from China. And they're far and away in the lead, with India, the United States being number 2 and number 3. The industrial emissions are concentrated in a fairly small number of countries, and if you count the EU as one policymaking area, you can target a very large share of the global industrial emissions by enacting policies in a fairly small number of policymaking venues, countries, and the EU. Here is a breakdown of the industrial emissions by industry and by emissions type. So you can see that this is, so non-metallic minerals, number 3 there is primarily cement. So you can see why my book had chapters devoted to iron and steel, chemicals, and cement. There's a big gap between the top three industries and everything else. The top three industries are about 60% of the world's industrial emissions. But a lot of the technologies we'll be discussing, including electrification, are not just for the top three industries. They are useful across all industries, and that makes them very powerful and useful. So this is again that overview of the high-level structure there, and now we're going to jump into electrification as an example to give you some insights into the technology side. So industry uses fossil fuels essentially for two purposes: energy and feedstocks. Energy is when you burn the fossil fuels, and it's overwhelmingly used for heat, to boil water, to drive industrial processes, etc. The energy to operate machinery like motors and pumps is mostly electrified already. Feedstocks are the fossil fuels that are used that go into making up products. So they're mostly in the chemicals industry where they make petrochemicals, and then they get converted on into output products like fertilizers and plastics. We can't directly electrify feedstocks, meaning replace feedstocks with electrons, because you need the atoms, the mass in them, to help make up the fertilizers and plastics. Although you could indirectly electrify them by using electricity to make hydrogen and capturing CO2 when you need carbon atoms and so on. This is a graph of the use of fossil fuels and electricity by industry in the United States. So the feedstock bar is at the top, but we're going to be focused, since this is electrification, we're going to be focusing on that middle bar, fossil fuels for energy. These two, the left two, are the heat used in industrial processes. The left one to power boilers, and the second to left for other process heating, which can be industrial furnaces or distillation columns or all kinds of things. Then this small number of uses on the right are mostly machine drive and other processes that are comparatively easy to electrify. For instance, with machine drive, you would swap in electric motors. And then non-process uses are things like heating, ventilation, and air conditioning for the building, or water heating for workers. And those can be electrified using building sector technologies. So when we're talking about electrifying industrial energy use, we're really talking mostly about the left-hand two bars, the heat for industrial processes. And if we're talking about heat, we have to look at temperature. So this is a breakdown of the temperature demand required for industrial processes in various industries. These data are from the EU, but the overall breakdown per industry would be similar in other countries and regions. The highest temperatures are in the top three industries that I mentioned earlier, the top three emitters: iron and steel, non-metallic minerals, and chemicals. And then much of industry has lower temperature demand. So there are there's 8 electrified heat technologies I'll discuss. I'll briefly mention heat storage and a couple heat replacement technologies. We won't have time to walk through every one of these technologies and how it works and what its efficiency is and what its temperature is. You can get the book if you want the detailed breakdown. But a sort of high-level summary would be: for low temperature, you can use waste heat pumps, which are most efficient, and waste heat recovery. At medium temperature, electric resistance, infrared heating, dielectric heating, which is like radio wave and microwave heating, like your microwave oven. And high temperature includes electric arcs, like arc furnaces and arc welding and plasma torches, electromagnetic induction, and then lasers and electron beams, which are good for precision applications like welding and cutting. What is the electrification potential across industry? Well, there's a study from Madedu et al. That looked at this for the European Union and divided it up where the y-axis here is the percent of industrial energy use by industry. This excludes feedstocks, of course. And then the x-axis is the share of electricity by industry. So you can see that most of industry can be electrified with technology, either already is electrified in white or can be electrified with technologies in 3 stages of technological maturity. Stage 1 are already mature technologies common across many industries, electric resistance heaters and so on. Stage 2 would be technologies that are already commercialized and used in some industries, but need industry-specific know-how to adapt them and use them more widely. So plasma torches might be an example here, where they're used for plasma cutting and various applications. They can be used to heat a cement kiln, and that's been demonstrated by a company called Cementa, but they're not yet used that way. So they would need to be you don't need to reinvent plasma torches, you just need to adapt them so that they can be used with cement kilns. And then stage 3 would be technologies that are at the R&D stage and still need some refinement. Hydrogen direct reduced iron and electrolysis of iron ore being examples. I won't read off everything in this chart to you, but it's just an illustration of how there are electrified technologies that exist that can meet any temperature demand. So it's something of a misapprehension in the industry that you need fossil fuel or hydrogen combustion to reach certain temperatures, but actually certain electrified processes reach higher temperatures than fossil fuel combustion. That'd be in the bottom row. And so you can meet any temperature requirement using electricity. So why is it that electricity isn't already used more widely, given that there's no real technical hurdles, no scientific problem with using it? And the answer is cost. This is the raw fuel cost. This does not account for efficiency. And this is 2019 after-tax values. The main comparison to make here would be electricity versus natural gas. Although coal is cheaper, it has to buy the coal, it has other problems, like it creates a lot of particulates and needs more expensive equipment to burn it. So its costs are actually higher than it seems when you look at the fuel costs. So in places where natural gas is reasonably available, like the United States, industries tend to prefer natural gas or electricity. And so this gap looks large when you're looking only at fuel prices, but then you have to account for efficiency because electricity is used more efficiently than natural gas or any other combustible fuel. This is just a slide with a reminder that you have to account for efficiency of use. So let's look at the efficiency of burning fossil fuels. So if you burn them, not all of their heat ends up being useful. There are some heat loss modes that have to be taken into account. For instance, there are hot exhaust gases from the combustion that escape out the exhaust vent. And then there's water. Even if you pre-dry the fuel, water is formed when you burn the fossil fuel or hydrogen. And water vapor has energy in it that you would could get out by condensing it. And that is typically part of the exhaust and is lost to the system. You can recover some of this later with waste heat recovery, but that's not all of it, and it's at lower temperature and is less useful and less valuable. If you could avoid the losses in the first place, that's better. One example furnace operating at 1340 degrees Celsius had more than half of the energy lost in the hot exhaust gases, another 10% to deal with moisture, 9% through furnace openings and furnace skin. So this high temperature industrial furnace was found to be 24% efficiency. Let's compare that to fossil fuels, green hydrogen, and direct electrification. So burning hydrogen has similar losses in that it makes hot exhaust gases and it generates water, but it has additional losses in creating the hydrogen, which in an alkaline electrolyzer can be up to 70% efficient. So you're looking at 16% efficiency for hydrogen in this sort of furnace, 91% if you could do a direct electrification, which has no exhaust gases, no water is formed. And then you have to look at the air pollution. So of course, fossil fuel combustion emits greenhouse gases and various air pollutants. Hydrogen emits nitrogen oxides. That's because it's splitting the N2 molecules in the air from the energy in the flame. Direct electrification has no air pollution. So given this efficiency advantage, that can help make up for a price gap and is a key reason why we should be using green hydrogen only when necessary. For instance, the feedstocks I mentioned, which cannot be directly electrified, that's one of the best uses of green hydrogen. There are other alternatives like fossil fuel combustion with carbon capture or bioenergy, potentially with carbon capture. They are covered in the book. They have their own downsides and limits. See the book for more. So the upshot is where we can, we should be leaning on direct electrification of industrial heat. Low temperature is worth another is worth a special look because boilers are usually used to provide low temperature heat up to about 165 Celsius or so is the cutoff I'm using for low temperature. And boilers are more efficient than the fossil-fired high-temperature furnaces like the one above. So I don't want that furnace to seem like a straw man argument. Fossil fuel boilers can achieve efficiencies of 90%, potentially even a little higher. If there's steam, it's 90 to 94. If it's hot water boiler, it's been demonstrated up to 98%, though real-world practice is lower. China, the boilers are on average 70 to 79% efficient, and that's where most of them are. But the electrified alternative, a heat pump, is more efficient also. So heat pumps can be more efficient than other electrification technologies because they don't create the heat from the electricity. They move the heat. A heat pump is similar to a refrigerator. So it can achieve efficiencies that are 200 to 500% of the input electricity is the output heat. This depends on the temperature increase the heat pump is delivering. The higher a temperature increase you want the heat pump to provide, the less efficient it is. So the highest temperature commercialized heat pump outputs at 165 degrees Celsius there. And you can see on the right with a heat source of about 35 C, which is a little bit warmer than room temperature, it will be a little bit more than 150, maybe 160% efficient or so. Whereas if you only need to, let's say you need to boil water and you have a heat source of 30 C, you can get between 2.5 and 3 coefficient of performance. So it gets quite cost effective. It cuts the amount of electricity you need to use down into so that you're using a third, perhaps, of the amount of electricity as you would with a resistance heater. There are plenty of applications for industrial heat pumps. This is a table from Arpagas et al., a paper that looked at industrial heat pump use. And here's a quick cost comparison that is from a report I did looking at a couple natural gas industrial uses, electric boilers, and then heat pumps at a couple temperature output ranges with an assumed COP of 3.7 and 2.2. This was using 2021 prices. So you can see that basically heat pumps are already cost competitive. They have a large overlap with the cost range of the natural gas technologies, even though electricity costs more. It's a good example of the efficiency making up that gap in fuel cost. And an important thing to note is that this table was made using the 2021 electricity natural gas prices, but by August 2022, natural gas had almost doubled relative to the 2021 averages used to make this table, which made heat pumps definitively cheaper. Natural gas prices are volatile. They move up and down with geopolitical events and technology and depletion of reserves and discoveries of new reserves. But electricity and is likely to decline in the long term because of solar and wind, which have zero marginal cost generation, making up a larger and larger share of the grid. Not to mention heat pump technology will continue to advance, and natural gas technology is already fairly mature. So in the long run, the trends will favor heat pumps. Briefly, this is another chart from that report showing some cost curves where, depending on the natural gas price and the electricity price paid by firms, whether the natural gas boiler or the 80 to 100 C heat pump or the 100 to 180 C heat pump is more cost effective. So the issue here is commercial readiness, as I briefly mentioned before. So all these technologies are based on understood science and engineering. Every one of them does have commercialized applications somewhere in industry, but specific products that replace combustion processes are not always available in every industry in a commercialized form. I mentioned the plasma torches example, where they can be bought commercially, but only one company has tried using them to heat a cement kiln. And that's because there hasn't been enough demand for electrified industrial equipment. So the equipment makers haven't prioritized applying these known science and technology principles to new types of equipment. So that's where policy can help. Policy can kickstart the demand, which will bring products to market, drive down equipment costs, improve efficiency, and help this process move forward more quickly. And that brings us to the last part of my talk today, which is covering policies. This is going to be a very high-level overview because the book has 4 chapters on policies of various kinds. It's a major focus along with the technologies and the industries. But due to time constraints, we'll have to focus on high-level things. So here are some near-term opportunities and needs. So you can go for efficiency emissions standards on industrial boilers, which are maybe the first easier thing to target, and then other sorts of industrial equipment, which are a little more diverse. You can also do efficiency standards. If they're not fuel specific, meaning you don't have one standard for natural gas boilers and a different standard for electric boilers efficiency, then you can comply with this standard by fuel switching. You can switch from natural gas to electricity, which is used more efficiently. And then that's even more true of the non-boiler types of equipment. If you set fuel-specific efficiency standards, then it may improve the efficiency of each type of boiler, but fuel switching may not be as viable a compliance option, and fuel switching is the goal here. Then there's green government procurement. That's what the government takes its money. The government is a major purchaser of industrial products, cement and concrete in roadways, and steel in government buildings and infrastructure, bridges. They can choose, they can set conditions like it has to be made in a low carbon way, and choose to purchase materials with some share of their budget. They can designate certain percentages of government spending on, let's say, steel. This percentage of government spending on steel has to be low carbon steel. They can even make tranches for a small percentage for very low carbon novel technologies, a larger tranche for a lower carbon than average, and then the remainder may not have that requirement to make sure that enough steel can be procured. There's lots of financing policies. You can set up green banks, which use lending mechanisms, or agencies can use lending mechanisms directly. You can give rebates for electrified equipment. Currently, there are rebates for electric vehicles, but you could have rebates for electric industrial boilers or heat pumps or furnaces. Subsidies for clean production per unit steel, let's say steel made using a zero carbon process like hydrogen direct reduced iron or iron electrolysis. Very new technologies that need to come down the cost curve and become more mature. Those subsidies wouldn't cost much for government because the quantities of steel made using those technologies are so small. And cost sharing, loan loss reserves, etc. R&D support, there's all kinds of policies there that can enable collaboration with national labs, government funding of R&D, and policies that ensure companies can hire science, technology, engineering, and mathematics talent. There's carbon pricing, which is in some US states and some countries, et cetera. There's just a table, I won't read it all off, but it's looking at some of the US policymaking authorities for certain types of policies that I mentioned before. And I'll close by thanking you for taking the time to listen. And there's so much more to say, and the book will cover all of this and more. So do check it out when it comes out. There's a mailing list where I'll inform you of the book's release. If you sign up, I can send you a link to that, or Todd can after. So thank you so much.
Thank you very much, Jeffrey. That was an illuminating and quick romp through some complex material, but I think you gave us a good sort of high-level discussion of this. And I guess I just wanted to say that it has been a pleasure working with Energy Innovation, and that I came to your work through your 2018 book, Designing Climate Solutions, which to me helped us offer a way to think about interventions in the policy space to help mitigate by looking sectorally at the low-hanging fruit for emissions reduction, because too much of the focus seemingly has been on nation states. And that, at the UN, it's all about national representations, and indeed, their nationally determined contributions are sort of the bricks of the lattice of the Paris structure for mitigation, the Paris Agreement of the United Nations. And so I guess a few questions arise, and I'd like to perhaps ask a few, if I may, and then turn to the audience for their questions, which they can write in the Q&A function area, which we'll get to. I'll take some of those in a few minutes for Jeffrey. I guess the first question is, it may be about complementarity of the nation state and sectoral approaches. As you mentioned, industrial emissions, about 45% are from China. And that seemed to be about 7 times the next largest on the graph you showed us, which were the US and India, and perhaps the EU as well. And it seems that if we take those as 4 actors and we put them in a room, we have nearly 2/3 of industrial emissions covered worldwide. And so I guess the question is about how to leverage the sectoral approach into national agreements, and whether the idea of climate clubs, which has been suggested with nation states, has any purchase for sort of at the sectoral level. And if trade associations, research groups, others by sector might or have considered any kind of international presence that might help drive down emissions. So I guess that may be a first question to ask, if you have any comment about that.
Sure. Policymaking is often made at the national or subnational levels, or in the case of the EU, there's a supranational body, but it's still a clear policymaking entity. Whereas large multilateral agreements at the UN have to be made real. They have to be enacted and caused to happen through policies at the national or EU level. I think that it is useful to focus on what countries or the EU can do to help decarbonize industry and the great benefits this would bring to those places. And it will bring benefits. It will bring investment that creates jobs and boosts GDP. And you can see this because, I think you mentioned the energy policy simulator. It's able to show this clearly, how the investment in shifting away from fossil fuels does tend to create jobs, not just in the investment in the new equipment, but because fossil fuels are a fairly capital intensive and low labor intensity industry per dollar invested in them. So you end up getting more jobs when you shift that spending to other things, whether it's savings for consumers or capital equipment or electricity. Internationally, there are things that can be done. A good example is the EU Carbon Border Adjustment Mechanism, or CBAM. So the EU has carbon pricing, and they want to make sure that their industrial producers are not disadvantaged by cheap, dirty materials like steel and cement flooding into the EU. So they will charge at the border for imports based on the carbon content if it's one of the covered materials. And the US has announced that they are working on negotiating coordinating tariffs with the EU on steel and aluminum that would be coordinated with the EU CBAM rate and mean that the US producers are not taxed, and dirty steel and cement from other countries is taxed upon entrance to the US. So you asked about these clubs or multinational agreements, and I think this is like the best current example, maybe. I mean, you can also say green public procurement can also be an international like purchasing club. So those are two. Border adjustments and government purchasing standards can be coordinated internationally, which links things into a larger market and makes the policy more influential, even on actors outside these borders, because a producer in India has to decarbonize its products if they want to sell it into the combined US-EU market.
Okay, great. Well, thank you. I guess more broadly, there may be questions in your policy prescriptions there may be questions about if US policy perhaps could or should go even further, which might be industrial policy to help induce greater efficiency in, especially, heating, I guess would be an area. I mean, you talked about the heat demand temperature, by certain industries, and certainly that iron and steel, non-metallic minerals, chemicals require above 500 degrees. And that my understanding previously had been that that fossil fuels were much more readily able to address that, and certainly they may be, at least at the natural gas level. I mean, as I guess you discussed, more cost effective certainly than electrification at this time. But I guess the question is, what if we invested greatly in this area and tried to push this forward, as China has done in, say, photovoltaics, or I guess especially Taiwan has done, and other green industries. I mean, how do we leverage the possibilities that exist and make them more concerted policies, and what is stopping us from such things?
Great question. And you're right that there's this sort of false impression that natural gas or hydrogen or combustible fuel needs to be used to supply these temperatures. Electricity can do it, and we already have all the technologies we need researched at various levels of maturity. But generally, at least we have each of those technologies in commercial use in at least one industry. So what we need is demand from industrial producers to purchase electrified versions of their equipment. We need cement makers to want to buy electrified cement kilns with electrified heating. And then cement kiln manufacturers will meet that demand It isn't even that hard. As Cementa demonstrated, they were able to attach plasma torches to a cement kiln and operate it, and it works. So what would drive the demand? That's policy, and to some degree technological development, like you said, with China driving photovoltaic prices down. We could do that with some of the electrified technologies, but the key cost isn't really the technology. It isn't really that a plasma torch is an expensive piece of equipment. The real driver is the fuel cost, the electricity cost over the lifetime of the equipment. For example, today's natural gas fired industrial boiler, over its entire 20 to 30 year lifetime, about 96% of the total cost of that equipment will be natural gas. 3% is the capital expense for the equipment, and 1% is O&M and staffing to run it. So so electricity, and some of those electricity prices in the chart are industrial retail rates. They're buying it from the grid, and there are lots of charges tacked on to grid electricity. So if an industrial firm wants to go off grid and have its own wind and solar and whatnot generation, they can access electricity at wholesale rates, which can be, I believe, 1/10 the rate of retail in some places. So it's a dramatic difference. And so one of the things we can do, in addition to all the industrial policies that I covered at the end of my talk, is also look at making electricity cheaper.
Okay, great. Thanks. Let me ask one or two more questions, and then I'll go to the audience. And again, I encourage people to submit questions into the Q&A area. We have a couple coming in, and a couple of my students are among the audience today, and a shout out to them, and the knowledge that they will come up with some good questions. No pressure. But another question, I guess, would relate to the electric grid, which, in many parts of the U.S. needs some changes. The commercial grid, which certainly some of these industrial processes would use, unless they do, as you say, go create their own system which they could do for wholesale costs of energy. But if they don't do that, or in the run up to that, until they're able to do that, if they're using the commercial grid, there's a lot of problems with the commercial grid, and also sort of how it's regulated from one state to the next in the U.S. I mean, the best example perhaps is, there's examples of shortages in places like California having to do mostly with distribution during peak hours, and solar energy has problems of delivery at some times of the day, right? On the other hand, it seems that there are other problems with the delivery of electricity in the commercial grid, such as in Texas, the private, the private incentives that have been structured into the grid by the regulatory structure there allowed for a pretty dramatic price spike during extreme weather events, I guess, during, if I'm not mistaken, it was 2021, when they had extreme weather and pretty radical price spikes. Are there changes that you think should be made to the electrical grid policies in, say, let's take the US, which maybe at least I'm more familiar with, but that would enable better use of these, industrial electrification, which is going to create a much heavier demand on an already burdened system, right?
Right. Yes, demand for electricity will increase with industrial electrification, and I'm not focused on the electricity side, grid side of things. We do have an electricity program. That said, one of the key things that the intersections of industry and electricity would be in the area of demand response and flexible load. So one of the electrification technologies on one of my slides was heat batteries. heat batteries are very useful because industry uses, as you saw, most of it, the fossil fuels it uses for heat. And electricity, if the industry is exposed to price fluctuations by hour, which is increasingly important as the grid gets more decarbonized, where the costs are higher in certain hours and lower in others because of availability of variable renewables. The one key thing to do is to pass on those price differences. So instead of levelizing it across hours, have it be higher in the hours where it's more expensive and lower in the hours where it's cheaper. And if someone buys power evenly in every hour, maybe the change doesn't matter to them. But for industry, they can buy more power when it's cheaper. They can store it in a heat battery, which is fairly inexpensive. It's just heat storage materials like silicon dioxide or graphite bricks and things like that, and then tap the heat when they need it in hours when electricity is more costly. So that can bring their cost of electricity down well below the average, as long as those hourly fluctuations are being passed through to the consumers, at least the industrial consumers, and not being levelized by the utility before being sent on. So that's one fairly simple thing that they can do to help. They can also provide different rates or rebates for flexibility services. So if the utility can call for ramping down demand in a high demand hour, and the utility and the industry switches over to their heat batteries or whatnot, they can be rewarded for that.
Okay, great. Well, thank you. Sorry, while you were finishing, I was trying to see if I could load so that we wouldn't have any problems loading slides. I think I loaded, right? Can you see my? Oh, okay, thanks. And I guess the next question, and I think my last one before I turn to the Q&A, is just to ask a little bit about the trade-offs between sectors. That is, mitigation is a problem which the Intergovernmental Panel on Climate Change has sort of divided into these 6 sectors, which your colleague Robbie Orvis very well sort of documented their share in the emissions problem worldwide, and here in this slide by nation as well. And it seems that indeed the sort of the orange industry, the top square across the board here, as well as electricity, the green one, are the biggest problems in, I dare say, most, if not all, countries. And indeed, this is from your 2018 book, cited in a book that I co-authored, a textbook. So, but showing even at that time that industry was a big part of the issue. And I guess the question is that the best place to make the largest investment as a collective, as we try to face this problem? It seems that the possibility, given that technologies exist to address problems, if they're more cost efficient, or if we find ways to make them so, perhaps with government action like subsidies, if we can do this, it seems that we can solve the biggest part of the problem through changes, especially in the industry sector, but also in the somewhat related electricity sector, or I guess as it's called, the energy sector, but which in part, a good part of that is also electrification with renewables. It seems that if we address the problems there, it almost means that we don't really have to do nearly as much in some of the more difficult sectors, such as, building retrofits or land use, which is extremely complicated. I don't know. Do you have any comment about that?
Yeah, I do. So One thing is, to address climate change, it is necessary to address all sectors, because there's a lot of emissions coming from each sector. And while they may not all be equal in priority, I don't think it's necessarily the best idea to play off one against the other when you could also be thinking about them versus other priorities that aren't mitigating climate change, and say we should focus more on mitigating climate change and less on such and such other thing. But I would draw a distinction between, so I put transport, especially on-road transport and buildings, into an easier to electrify category. Buildings aren't that hard. You can use heat. Their major demand, their largest demand is for space heating and cooling. Cooling is already largely electrified. Space heating, you can do heat pumps, which are efficient and can use the same ductwork as a furnace or an AC, or you can use ductless systems, which are mini splits, common in Europe, growing in popularity in the US. Water heaters too can be heat pumps or on-demand electric resistance water heaters. While you can improve insulation, that's harder. That requires a bigger retrofit. It's not necessary to electrify. And vehicles, I mean, this isn't my specialty, but we can see the growth of electric vehicles, and you can see in the energy policy simulator tool Robbie mentioned and others that they're growing a lot, even in the business as usual case, and can be further accelerated due to policy. If you're talking about aircraft or long distance shipping, that's where we may need some biofuels, but the amount of fuel we need is small enough that we should be able to address it with biofuel. And so I don't find those to be as challenging as electricity and industry. Those two are the biggest pieces. And industry, I mean, while challenging, there is a roadmap for how to get there technologically and policy-wise, and that's why I wrote an entire book about it, laying out the roadmap. It's hard to sum it up in two pithy sentences, but it's about identifying this set of technologies and then the policies that will help get those technologies commercialized and deployed at scale.
Okay. Well, thank you. I mean, I guess, unfortunately, this webinar format does lend itself to short, pithy statements, but you've offered us plenty in the course of this this period. So thank you. And I'm going to turn now to some questions from the audience. We have a couple. One is, how can civil society incentivize or lobby for some of these policies? What do you think of that? General climate movements enough, or targeted sectoral interest group approaches, trade associations? What do you think?
It's a good question. I think more than one route could be helpful. In general, you can look at the scope of the span of decision makers. Who makes these decisions? Well, policymakers make the immediate decisions to make policy, and there are the ways to lobby them, writing to them. But there's also industry. So industrial facility managers decide what types of equipment to buy or use. And industries respond to what customers want. So you can also push for industries to demand electrified technologies and other zero carbon processes, and to push for policies that do. So industries can see competitive advantage if once they are doing something, it's often in their best interest to push for a policy that requires it. So if here's an example, a real world example from, I spoke to the head of research and development at Cummins, which is an engine manufacturer.
Mhm.
And they felt that so they pushed for tougher standards on efficiency of diesel engines, which is their own product. And you'd think, why would they want tougher regulation on their own product? Why wouldn't they just make the engines they want to make? Well, the head of R&D said, we feel that our research and development operation is a strength at Cummins compared to other engine makers. And so when a new standard comes out, or we see it will come out, our R&D operation kicks into gear. We figure out how to meet it at lower cost than our competitors can because we have superior research. And so then when the standard hits, the competitors have to do more expensive things to meet it. They have to raise their prices more, and Cummins gains market share. So they saw it as leaning into their competitive advantage. Now that's a case with a combustion engine, but the same thing would be true with industrial electrification. So if a company has already electrified their processes, or if they think they can do so cheaper than their competitors, they may be in favor of pushing policymakers to mandate it or enact tougher standards so that they can gain market share from their competitors. And this is a way to get companies on your side. Find the leaders, find the ones that can gain some financial advantage from doing so, and push them to join you in a climate movement. Their motive may be financial, and that's fine. Just as long as they back you with when you come to policymakers, and they're more likely to listen if it's not just climate people want this, if it's also climate people and innovative American businesses want this.
Okay, great. Well, thanks. It's good to know that. I suppose you speak about civil society, but also, I guess, about sort of people as consumers and sort of, trying to shoot for higher standards. I think that's an interesting approach to that answer. So thank you for that. All right. We have another question, which may be a little bit out of your wheelhouse, but it's about maglev versus TGV or other type of high-speed train. I don't know if you have any comment about that, but it also leads into another question regarding sort of nuclear fission, and I guess more broadly, do you see nuclear power as part of the solution to the energy mix? It seems that there's a contentious question about whether nuclear is clean or whether it's renewable. Certainly it's renewable. Maybe it's not as clean. What do you think? Or maybe I'm mischaracterizing it.
I think that nuclear power does have a role to play, at least over the next several decades, in decarbonizing the economy. One large issue with nuclear power is the cost of constructing new nuclear power plants, which has actually gone up over time well, for one thing, safety standards and other standards have gone up, regulatory oversight has gone up, the cost of input components and things has gone up. And it's just not financially competitive now that we have all of these cheap renewables coming online. If you want new zero carbon electricity, we're at the point where building new wind and solar is actually cheaper even than operating existing coal plants. It's not cheaper than operating existing nuclear plants in many cases, although it may increasingly be getting to that point, but it's certainly cheaper than building new nuclear plants. And so they become very unaffordable. And I don't see that changing because they're in this race against renewables where they have this very strong, very low cost competitor. And so my view is we should continue to operate the ones that do exist because the capital investment has been made, and we don't yet have a decarbonized grid. And if they were to go offline, that energy would be replaced to a significant degree with additional fossil fuel combustion, which would be damaging to the climate and the future of humanity. But I just don't see it as feasible, at least under the current technology, and maybe never, to build much in the way of new ones because of economics. They're just going to be not that competitive against cheap renewables.
Okay. That's a fair answer. It raises another sort of question, which is a broader question about the sunk costs that we have in sort of producing, energy to run industrial processes, particularly based on coal, which is no doubt the worst offender, and which is the basis of many of the plants, industrial plants in China, India, some in the US, elsewhere, and apparently still on the increase in China. And so I guess the question more broadly about the sunk costs of the fossil fuel processes and how to overcome those, may add an additional layer of cost to the calculations. And I don't know how you account for that. And also, I guess there's, of course, a large fossil fuel industry and lobby, and there's subsidies. There's a very large support system and a long-standing interaction between fossil fuel industries and, say, government. I mean, elected officials get support. I mean, they're a prominent, one of the top 3 or 4 probably most prominent lobbies in the US, at least, right? And in other countries as well. Do you have any comment about how to deactivate those political interests? And will it take more than just continuing to lower costs of renewables? I mean, that's certainly the emerging solution, is that it's becoming so cheap that it's undeniable. On the other hand, there are still these entrenched interests. How do we unentrench them? If you have any comment about that. I know it might require more speculative answers than your models would lead you to, but I don't know if you have any comment about that.
Yeah, it's an important issue and a good question. So the part of the answer is cost, and you asked about displacing fossil fuels in industrial processes was the first part of the question. I'll comment on that briefly. These standards that we're looking at probably are standards that apply for the most part to newly sold industrial equipment, maybe entirely to newly sold, not to existing. So an industrial boiler, has a lifetime of 20, 30 years. When it next gets replaced, maybe it gets replaced with an electrified version. So if you wait until its natural replacement cycle, there is no added cost for the replacement, or even for shutting down your, you have to shut down the production line maybe to remove the old piece of equipment and install the new one. But if you were going to do that anyway, there's no added cost to doing that either. So working with the timelines of industrial equipment replacement, which amounts to mostly putting your standards and requirements on newly purchased equipment, is one way to minimize those costs and disruption to industrial processes. Which is not to say there's nothing else that needs to be done. For instance, maybe they need more electricity capacity coming into their facility, so they might need a new line or a new transformer, but it minimizes it to work with their replacement cycle. That's the first part of the question. The second part is how to achieve political change. I think it's important not to be defeatist, to understand that this is something that is happening and that we can push it forward faster. There's already been a lot of progress, faster than many people believed possible, toward renewable energy, toward electric vehicles, which are making up a larger and larger share of sales in the US and globally. And there's no reason to believe the same thing can't happen in industry. It can and it will, because ultimately decarbonizing the economy is necessary to preserve a livable climate. And that's what it will ultimately come down to. And so there is a lot of political support for this. And I believe this will only grow over time as A, renewable technology costs come down, B, the climate damages become more obvious to more people, and C, there's a larger political momentum which is created as companies and others that get behind the renewables have their own lobbying operations that scale up with the size of those industries and so on. So there's at least three factors that that will push this forward, and it's our task to try to accelerate all of these trends. One thing I'll point out is that fossil fuels are artificially cheap today because they're not paying for the damages they're causing, which is something that if you want to have a fair and level economic playing field, you shouldn't be allowing one product to cause harms and not charge for that. And this includes public health harms. So when you burn fossil fuels, it creates particulates, it creates nitrogen oxides and sulfur oxides. And there's very solid research that will tell you how many thousands of Americans or US residents die every year because of these fossil fuel emissions. It's a large number. And each life, there's a VSL, value of a statistical life, that is used in regulatory rulemakings to monetize this sort of thing. If you were to allocate those costs to the fossil fuels, they would already cost much more than they do today, simply because they're covering the costs of the US people they are killing. So it's not, it shouldn't be seen as radical to want to shift to clean energy. It should be seen as the most reasonable, humane, and prudent thing to do, both for people alive today and for the future of our society.
Okay, thank you so much. On that note, on the idea that that we are making strides and that we can make more, and that indeed the solutions you suggest are reasonable, humane, and prudent. I think it's a good moment to thank you very much for joining us. See if you have any other comments that you'd like to make. If there are, please go for it. But I guess also lastly to thank Energy Innovation, and to remind people that a Zero Carbon Industry is coming out from Columbia University Press, and that if you have a link that you perhaps want to put in the chat for the policy simulator, that would be great. Oh, also for the book.
This is sent to the host and panelists, so you'll need to repost it if you want everyone to see it. It's the link to the sign up where you'll learn about when the book comes out. It's a mailing list that it only will get like an email when we release major products, maybe 4 times a year. So it's the best way to be informed the moment the book comes out, is to sign up for that email list. So the Energy Policy Simulator has its own link, energypolicy.solutions, easier to remember than the mailing list one. I can put it in the chat.
All right. I wonder if we can put, I tried to put the link for the newsletter in the broader in the broader chat and wasn't able to do so.
Maybe SPA Events did.
Yeah, let's see.
And there's to follow up, energypolicy.solutions is the link to the simulator you asked for. So I put that into hosts and panelists, and SPA Events can reshare that one too.
Okay, thank you. That would be great.
Or just type in your browser energypolicy.solutions. It's easy. That one's easy.
Great. All right. Anything else that you would like to add?
Nothing else right now. Just wanted to thank you for the opportunity to come on and speak, and for all the excellent questions. I appreciate it.
No, thank you very much. And we very much appreciate the work that you're doing and that Energy Innovation is doing. And we look forward to continuing to follow it. And we will have a final discussion webinar on May 9th at 1 p.m. Eastern time. We'll send out more information about that. And we look forward to seeing many of you again at that discussion. And again, thank you to Jeffrey Rissman for his very comprehensive, in a short amount of time, summary and presentation of some very complicated issues in some very lucid, broad strokes. So thank you very much. And again, best wishes and thank you. And we'll look for the book.
Thank you so much, and appreciate it. So long.
Be well. Thank you.